So what we have here is the Hamiltonian for our harmonic oscillator system. And what we've got here is the specific heat for our harmonic oscillator system. And we've not yet evaluated this derivative. By not evaluating the derivative, we can do some expansions to hopefully do some approximations, because once we evaluate the derivative, it's a bit of a pain to plug things in. A bit of a recap here is that we've got this function, which is the Bose-Einstein function, which helps us figure out the number of bosons in which state. And we've got this beta term, which is 1 over kBt. Now, to look at this section of the specific heat, what we actually want to do is take the derivative there, but we almost want to take some sort of other term or turn it into something different. So what we're going to try to do is make this into something different. Now that we realize off the start that this 1/2 term, the derivative of that's 0, so it doesn't matter. What we really care about is finding the derivative of ns of k with respect to t. That's our goal. So we want to get this. The problem is making this nice. So what we'll do is we're going to start off by taking this ns of k term, and we're going to make ns of k equal to just 1 over e to the x minus 1. And the substitution that we're doing here then is x is equal to beta h bar omega s of k. Now we know that there exists such a Taylor series expansion for e to the x. E to the x is equal to 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial and many other higher order terms. So if I was to plug that in there, what we would get is ns of k is equal to 1 over 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus many other terms, and our last little bit there was minus 1. And we can see we got 1 there at the beginning, and after our infinite series we have a minus 1. So this nicely becomes 1 over x plus x squared over 2 factorial plus x cubed over 3 factorial plus an infinite number of more terms. Now, everything in the denominator here has a factor of x. So what we can do is we can approximate this still. We can say, well, this is actually 1 over x times 1 over, now it is 1 plus x over 2 factorial plus x squared over 3 factorial plus many other higher ordered terms. And what this is starting to look like now is another series which we actually know about, and that is a geometric sum. And we know that 1 over 1 minus r is actually equal to the sum of r to the n from n equals 0 to infinity. So what we can do here is make a substitution for r here. And our substitution here for r then is, well, r has to be equal to negative x over 2 factorial minus x squared over 3 factorial minus all the other higher order terms. Now in doing so, we get this lovely expression. We get 1 over x times, and now in the numerator, we have 1, which is anything to the power of 0, minus x over 2 factorial minus x squared over 3 factorial minus dot 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 all these other higher ordered terms. And this is all our r term to the power of 1, an infinite number of terms to the power of 1. But we also have to add in the next power, which would be Well, I have to take all these terms, again, that appear here and square them. So I'm going to have, again, a minus x over 2 factorial minus x squared over 3 factorial minus all the other higher ordered terms squared. Plus, I need to have, again, the same infinite series, but to the power of 3. And so forth and so forth. And this is all within this bracket. Now, if I'm thinking about this in the right way, all of these can only be done if our x is very, very small. We can't do this unless our r term, for this sum to be true, to converge, this r has to actually be less than 1. Or greater than -1. The magnitude of this has to be between 0 and 1. And in fact, for this Taylor series expansion here to work, we know our x also has to be very small. So, if I know x is very, very small, when I look at these terms, I know that if I take the square or the cube or any other higher ordered terms, I'm actually getting a smaller and a smaller and a smaller number. So my next real approximation here is that I'm going to be able to take this and say, well, that's 1. Or I'm going to get this first order term, 2 factorial minus x squared over 3 factorial. But a lot of this other stuff's going to go away. Now, this next set here, these are all negative, but if I have to square them, they're going to come out positive. So I'm going to get a positive x squared, and 2 factorial is just 2. And 2 squared is 4, so I'm going to get a positive x squared over 4. But everything else is going to be too small to worry about. But I have those terms, but they are just too small. So now I've got this, and what I'm going to do with it now is, okay, I'm going to try to clean it up a bit. What I can do is I can notice that I've got 2 squared terms, and this in the bottom is 3 factorial. And 3 factorial is 3 times 2 times 1, and that is 6. And 6 and 4 have a lowest common multiple of 12. So if I take this number, I can get 2 of these. And for this one, for 4, I can get 3 of these. So I should have 3 of these minus 2 of these. So I'm going to get 1 over x of 1 minus x over 2, because 2 factorial is just 2. And I'm going to get plus x squared over 12 plus higher order terms that are just too small to matter. So I'm saying approximately. And now I've got this term. Now, I've got this term, and what I can do is I can substitute back in my x value, and I can start taking some derivatives. At this point, we want to try to take this derivative because we got as far as taking the derivative of ns of k. And we said that ns of k, if we substituted the exponents term here, our natural exponents is power, which is beta h bar omega s of k. We were able to approximate it if we have just e to the x minus 1 here is we have this whole thing as 1 over x times 1 minus x over 2 plus x squared over 12. So what I'm going to do now is I'm not actually going to just plug my x in right away. I know from calculus that what I can do is if I'm going to take a derivative, it may actually be easier for me just to leave this in terms of x, take the derivative with respect to x, and then apply the chain rule. So what I'll do here quickly is, all right, I have x as beta h bar omega s of k. Well, what I can do here is I know that beta is actually 1 over kbt. So what I've got here is h bar omega s of k over kbt. And what I can do is, if I want to say take the derivative with respect to x, well, if I look here, if I'm taking the derivative with respect to x, of x with respect to t, I've got a T on the bottom. That's the only T I see. So what I've actually got here is minus h bar omega s k over kb. Now that negative comes from the T, which is in the bottom, and I have to subtract 1, and then I can say this is my dt. And I can throw my beta back in because beta is just 1 over kbt. And if I do just 1 beta, I'm going to have this whole thing over t. What I can do is I can multiply the top and bottom by kb to give me a dx is equal to minus kb h bar omega s of k with a beta squared dt. Now this takes our substitution term here and gives me something that I can make a derivative out of. So I can take dx by dt and have this term. Now, going back to this thing here then, if I was to take the derivative of ns of k with respect to t, what I can do now is apply the chain rule and say that that is actually the derivative of ns of k with respect to x times the derivative of x with respect to t. Now, I've already said that this is approximately true, so once we've introduced this idea of approximately, well, why make it any harder on ourselves at this point? So let's just be really approximate. If I'm going to be really approximate, then nx of k is really just, let's see here, x is a small number, and as x gets bigger and bigger and bigger, it gets smaller and smaller and smaller. So what if I just took the first term? The first term is just 1 over x. So the derivative of this with respect to x, well, that's just going to be negative 1 over x squared. And that's not too tricky. So now if I was to sub back in my x term, I could do so, and then I can multiply by the chain rule, and I've then found the derivative here. So this, with respect to x, is that, and what I'm going to do now is then say, well, if that's x squared, then dns of k with respect to t is then approximately, because this is all approximate here, this is going to be approximately equal to negative 1 over my x substitution squared, which I'll need to plug in still, times the derivative of x with respect to t, which we then found up there, which is our negative h bar omega s of k beta squared kb. So I now need to plug in my x term. My x term is beta h bar omega s of k. So this is actually equal to, well, let's see, my negatives are already going to cancel. I've got in the top here my term right here, which is h bar omega s of k beta squared kb. And on the bottom, which I have squared, is beta h bar omega s of k, all squared. All right, so with this here, I can right off the bat see that my beta squareds are going to go away because that's a squared there. So this guy's gone. Now I've got my h bar. Well, my h bar here is squared. This is just a single h bar, so it's going to stay. I've got one of these, but two of these. So I can now say that this is going to be approximately, I've got a kb on the top, but on the bottom it looks like I have h bar omega s of k. So I can take this first approximation for the high temperature, and I can go back to the very beginning of what I had for specific heat. And the very first specific heat approximation here was Cv is equal to 1 over V. The sum for K's, the sum for S's of h bar omega s of k times my derivative of this ns of k with respect to t. But we just took approximation for that. So that approximation says that that's kb over h bar omega s of k. So that cv is approximately 1 over v, the sum of k, the sum of s, h bar omega s of k, this guy, which is kb all over h bar omega s of k. Well, isn't this convenient? I can cross these guys out, and I'm now down to cv is approximately equal to 1 over v, the sum of k, the sum of s of kb. So at this point, I can actually take a sum because this doesn't depend on s or k. So I can count through my s's, which count the number of different frequencies we care about. And we actually care about a transverse, and a longitudinal waves here, or frequencies for our phonons. And our k's, well, they just go from 1 to n. So what happens is my kb comes out. This goes from 1 to 3, so I've got 3. And this is up to n, so I've got n. Now, if I was to worry about for the volume of whatever object I'm caring about, this tells me that the specific heat for a particular object is going to be approximately 3n kb for a volume of some object. So you take it for the whole volume, that's what you're going to get. And this agrees with the law of Dulong and Petit. So this actually agrees with the classical law. Now we can make a correction to this law if we were to include any other term from this guy up here. If we look at any other term up here, then we can start to make a correction. And if I look at the first, I only use this first term. If I was to have expanded to another term or another term here, then we get a better correction. Now the first term, if I expand to it, I'm going to get x divided by x goes away, hopefully, if none of those are 0, which they shouldn't be. And all that's left is a factor of minus half. The problem with the factor of minus a half is when I take the derivative of it, it goes to 0, it goes away. So this is not the term I care about. But the term I will care about is this one, this x squared over 12. So I can just find the correction very quickly by just taking the derivative of that portion, because the derivative is a linear operator, and what happens is I can just tack this derivative on then at the end. So I can just take this derivative, and with this small correction added on to everything else here, we can see if there's any change. So what I'm going to do now is I take the derivative of this term here, so I expand it out, so I'm going to have x over 12. So the derivative with respect to x of x over 12 is just going to be equal to 1 over 12. Okay, so with that 1 over 12, what I can now do is I can take this correction term and I can say, well, if that was the ns of k, then I still need, and that's my derivative, then what I'm looking at here is d of ns of k as a correction term with respect to t is going to again be the d of ns of k by dx times dx by dt, and I already know what that is, so I'm now just plugging in my correction term. So I've got 1 over 12 times my other term I found already, which is negative kb h bar omega s of k beta squared right here. So this term times that is my correction term. So what I'm going to do with this correction term is, again, put it behind our term for the specific heat. So our specific heat is equal to 1 over the volume, the sum for k from 1 to n, the sum for s from 1 to 3, times h bar omega s of k times this, where I've got kb h bar omega s of k beta squared over 12, and it's negative. Now I can see if I can get rid of anything here, and it looks like I can't, but I can incorporate that h bar omega s of k right back inside. I can throw it into the brackets here by and essentially square it. So I'll have a h bar squared omega s squared, and I'm going to have a beta squared. Well, that's looking pretty nice already. And it looks like my KB in the 12 I can pull out. Well, what this says then is that this is essentially equal to KB over V with the term of 12 here. So negative KB over V times 12, the sum for K, the sum for S of H bar omega S of K times beta all squared. And what I can now do is take both of these terms together to get a final form for my specific heat. So the specific heat high temperature approximation is approximately the first term, which we got. So we got 1 over V KB times 3N, which is the classical, plus this correction term, which is going to be 1 over V times KB over 12. Now this is negative, so when I say plus, I'm actually meaning negative. And then that's going to have the double sum for K, for S, and I'm going to have my H bar omega S of K times beta all squared. And this is my correction term in high temperatures. Now the only reason we could do all this is because our x, when we expanded our polynomials at the very beginning, is supposed to be small. It's supposed to be close to 0. And the only way that we can say that this is a high temperature approximation is that what I substituted for x in the very beginning, well, that term that I had for x was x is equal to beta h bar omega s of k. And that was equal to h bar omega s of k all over kBt. Now, we said that x had to be close to 0, and as temperature gets large, as this t term here gets really, really big, well, x has to get small. So in the high temperatures, this works. You can do these approximations, you can make these substitutions, and everything should work.